Okay, today we're going to talk about continuous probability distribution functions. Okay, we talked about in the last chapter, chapter 4, we talked about things like the binomial distribution, the hypergeometric distribution, and the Poisson distribution. Those were discrete probability distributions. Okay, this chapter 5 is going to be about continuous probability distributions. So let me write down what that means. Okay, it is a continuous function that is non-negative. So a continuous non-negative function where the total area under the graph equals 1. Okay, and the area under the graph between two x values represents the probability of the continuous random variable falling between those two x values. Okay, now let me give you some examples of what we're talking about here. Okay, I'm going to give you 3 examples. Okay, the first example is called a uniform distribution. That's where the probability of a random variable equaling a certain value is the same probability for all values. Okay, so that means that the graph will be constant. All right, it'll be straight across. So look at this example here. Can you figure out how tall this must be? Let's figure it out. We can figure it out. Let me ask you a question. Where is this graph starting? It's starting at 2, right? Where is it ending at? Okay, it actually doesn't say exactly, but I think that's probably about 8.8. Okay, which means that this distance across there is a length of 6.8. Okay, now remember what I said about probability distributions. The area under the graph totals 1. So this rectangle here has a total area of 1. Area equals length times width. Okay, so therefore in this case, question mark times 6.8 has to equal 1. So what is the value of question mark? It's 1 divided by 6.8, which equals I'll round off to 3 decimal places, okay? It's about 0.147. So that's how tall this rectangle must be. I rounded off to 3 decimal places. Okay? All right, now let's erase some of this stuff here. Now that shaded purple part, this is what you need to know. This is going to be really important for almost everything we do from this point forward. That shaded purple part represents the probability of our random variable x being between 3 and 6. The area under the curve from 3 to 6 represents the probability of our random variable falling between 3 and 6. Okay? And in this case, based upon what we said here, that the height of the triangle is about 0.147, that means that this probability would equal approximately 3 times 0.147, and that equals 0.441. Okay, so this area here, this purple area is 0.441. So whatever variable this is measuring the probability distribution for, that variable has a 44.1% chance of falling between 3 and 6. Okay? Let's do a problem out of the book. Okay, here's example 5.2. And this is off of page 247. It says the amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes inclusively. Okay, let's draw a graph of that distribution. So look at what it says. It is uniformly distributed. So that means the graph of this distribution will go straight across. Okay. Let me draw the axes. Okay, and then what else does it say? It says between 0 and 15 minutes. So that means we go from 0 to 15, and we draw a constant function straight across. There's the probability distribution. Okay? Now, just for sake of making things easier, let's go ahead and mark off 5, 10, and 15. Okay? Now, how tall is that rectangle? Okay, we'll figure that out just like we did before. Remember, the whole area under the curve represents 100% of the possibilities, and so that means that area is 1. Okay? So if the whole area here equals 1, and the width of that rectangle is 15, then the height must equal 1 divided by 15, right? Because the height times the width equals the area. So that means the height equals 1/15. All right, we won't round that off this time. Let's leave it as a fraction this time. Okay. All right, so there is the probability distribution. If you wanted to find the probability of waiting for the bus a certain number of minutes, you could use this distribution to find that. Okay, now you could not do this. What if the question was different? So the question says, what's the probability a person waits fewer than 12 minutes? What if the words fewer than were not there? Then you could not answer that question. What's the probability that a person waits 12.5 minutes? You would not be able to answer that question given this information, because that's asking you to find the amount of area right here. Well, there's no width to that. And so there is no area there. But that's not what they asked, is it? They asked, what's the probability that the person waits fewer than 12 minutes? So that means they're asking us for the area, not 12, but 12.5. They're asking us for the area up to 12.5, from 0 to 12.5. Okay, well, that's easy to find, isn't it? Let's actually, in fact, I'm going to erase those diagonal lines and we'll just do the calculation right. Whoops, I did not mean to do that. We'll just do the calculation right there in the picture. What's the area of that rectangle there? Let's do this. We'll shade it so that way we can still see it, but shade it with a light color so we can still write on top of it. Okay, so what is that area? That area has a height of 1/15 and a width of 12.5. So what's that equal? That's 1/15 times 25 halves, which equals how much? Go ahead and work that out. And isn't that going to equal 5/6? You see where I'm getting that 5/6 from? Because you can do some reducing here. 5 goes into 25 5 times, and 5 goes into 15 3 times. So on the top we have 1 times 5, and on the bottom we have 3 times 2. So what we can say is that that x is the amount of time somebody has to wait for the bus, and we can say that the probability that x is less than 12.5 minutes is 5/6. Okay, that's how that works. Now we're going to answer another question about this same probability. By the way, our answer to question A was 5/6. If you want to write that as a decimal, that's about 0.833. Okay, so 83.3%. That's your probability of waiting less than 12.5 minutes. Okay, now B. On average, how long must the person wait? Find the mean and standard deviation. Okay, so you need to know the formulas for this. When you have a uniform distribution. The formula for the average, let's make that a little bigger. The formula for the average equals A plus B over 2, where A is the left endpoint and B is the right endpoint. Okay? The formula for standard deviation for a uniform distribution is the square root of B minus A squared over 12. The bottom is always a 12 when the distribution is a uniform distribution. Those two formulas are at the top of page 247 in the book. Okay? So let's answer that question. Part B. What is the average wait time? So the average wait time would be 0 plus 15 over 2, which is 7.5. So the average wait time is 7.5 minutes. You need to write the word minutes, otherwise there's no meaning there. If someone said, what's the average wait time, and he said 7.5, that would not be telling the person anything useful at all. Because they might say, oh, 7.5, that's not too bad. Well, maybe you mean 7.5 days, right? Or maybe you mean 7.5 seconds. Those are very widely apart, aren't they? So, in other words, to just say 7.5 without saying 7.5 what is a meaningless answer. Okay, so you need to say the units. All right, let's find the standard deviation. Again, here's the formula right there. Okay, so the standard deviation will be the square root of 15 minus 0 squared over 12. So that is the square root of 225 over 12, which equals let's see, that's going to be approximately, I mean, I can tell you exactly. The square root of 225 is 15, and the square root of 12 is 2 root 3. Okay, so but it's more useful to figure out what that is as a decimal. So let me calculate that here. That is about 4.33. Okay. Minutes. That's about 4 minutes and 20 seconds. Okay. And now let's do one more example about this same situation. Okay, question C says 90% of the time a person must wait falls below what value? Okay, what are they talking about there? Here's what they mean. They're saying that if you start at 0 and you go across until this area equals 0.9, where would that shaded rectangle stop? That's what they're asking. Okay. If you want this area to equal 0.9, the question they're asking is, what is that value right there? How many minutes Okay, well, this is actually very straightforward. We know the height of that rectangle is 1/15. So we have 1/15 times the width equals 0.9. Let's write that as 9/10. So that means the width that we're looking for is equal to 9/10 times 15, which equals 27/2, or 13.5. Okay, I could say this. I could say the probability that x is less than 13.5 equals 0.9. Okay? And the answer to that question, we would say x equals 13.5 minutes. Okay? So that is how you work with a uniform probability distribution. Okay, the second kind of continuous probability distribution that I want to show you is called an exponential distribution. Okay, if you've taken a college algebra class or a calculus class or pre-calculus, anything like that, you've probably seen exponential functions. They go like this. Okay, and the equation for an exponential function always looks for a, I should say this, I shouldn't say the equation just for an exponential function. I should say the equation for an exponential probability distribution always looks like this. Some number, we'll just call m, okay, times e to the power negative m times x. Okay, this number m, which shows up in two places, that's called a special name. Let's see, I'm trying to decide what, let's use red. That's called the decay parameter. Okay? And here's something really interesting. When you have an exponential distribution, the average mu is simply equal to m. Sorry, it is not. That's 1 over m. Okay? And the standard deviation, this is what I meant to say a second ago. The standard deviation equals 1 over mu. And what would that equal if mu is 1 over m? Then the standard deviation just comes out to equal m. Okay? And again, the area that's shaded under here tells you the probability of the variable landing in that range. So let's use this to answer some questions to get some practice. Okay, look at these two examples right out of the book on page 250 and 251. Okay, it says let x equal the amount of time in minutes a postal clerk spends with a customer. The time is known from historical data to have an average amount of time equal to 4 minutes. Okay, the question cuts off there. Let me write down what it is that they're actually asking. The actual question says, find the probability distribution. If it is known to be exponential. That's the part that got cut off there. Okay, so let's answer that. So if it's exponential, we know what shape it'll look like. It'll look like this. Okay, and we also know the formula for that function. Remember, it is m times e to the negative mx. And also remember that m equals 1 over mu. Let's go ahead and put that here then. And look in the question, they tell us mu. It says the average amount of time is equal to 4 minutes. So mu is 4. So there's our probability distribution right there. Okay? Now, let's answer example 5.4. It says, using that information, find the probability that a clerk spends 4 to 5 minutes with a randomly selected customer. They want us to find the probability that X is between 4 and 5. Okay, so we need to talk about how are you going to figure this out. Okay, I can draw a picture for you. What they're asking us to find is they're asking us to find how much area is in this shaded part right here. And if you know how to do calculus, integrals, then you could calculate that using calculus. But this class does not assume that you know how to do calculus. So how are we going to figure this out? Okay, this is what we're going to do. So here's what you need to know. For an exponential probability distribution, okay, let's find for this function 1/4 e to the negative 1/4 x. Okay, let's find the probability that x lies between 0 and 5. Now again, you probably don't know yet how to calculate that, but I'm going to tell you in just a minute. If you've taken calculus, then you might remember. Okay? So here's the answer. That is always going to be equal to 1 minus e to the power negative, in this case 5, times m. Well, let's not forget the m. Sorry, let me put the m in there. Okay. Let me write this as a formula. What I'm trying to tell you is that the probability that x is less than, let's say, some number k, for an exponential distribution, that's always going to be equal to 1 minus e to the negative mk. All right, so for us, we have m is 1/4. So that area from 0 to 5 equals 1 minus e to the power of negative 1/4 times 5. That's a computer problem, okay? Not computer, calculator. I mean, you could use a computer if you want. But I'm going to plug this into a calculator. I'm going to do 1 minus e to the power of negative 5/4. And that comes out to be approximately 0.713. Okay, now let's find the area under the graph between 0 and 4. Using this same formula right here, that's going to be 1 minus e to the negative 1/4 times 4. Okay, you plug that into a calculator or a computer, and you're going to get approximately 0.632. So, what would be this area? Well, if the area from here to here is 0.713, and the area from here to here is 0.632, then the area between 4 and 5 would be 0.713 minus 0.632. And what's that come out to be? Let's just calculate that. Whoops, I messed up. Hang on a second. That is 0.081. Okay, I'm going to write this down, then we're going to review that problem again. Okay, let's write this down. 7.713 minus 0.632, and so that's 0.081. Okay. So let's just review again quickly. How did we do that? Okay, so you do this. Let's erase this. So you calculate the probability that x is less than 5 equals 1 minus e to the negative 5/4. And that's where we got 0.713. And then you do the probability that x is less than 4 equals 1 minus e to the negative 4/4, which is negative 1. And that comes out to be 0.632. So the probability that x is between 4 and 5 comes out to be 713 minus 0.632. And that's where we got our answer of 0.081. Okay, that's how you work with exponential distributions. Let's do another example of an exponential distribution. Okay, let's look at this example, 5.5, which is spread across pages 251 and 252. Now there's a typo. It says parts A, B, and D. Of course, that should be A, B, and C. Okay, but let's read the information and then answer these three questions. It says, on average, a certain computer part lasts 10 years. Okay, let's write down right now before we forget. Mu equals 10. Okay, years. I better write that. Okay, the length of time that a computer part lasts is exponentially distributed. So that means its graph will look like this. Okay. All right. In fact, let's go ahead. I'll draw that a little bit more precisely, and let's write down the formula, because all we need to know is two pieces of information. We just need to know that it's exponential, and here's the average. That's all we need to know. And I can say that the formula is, do you remember the formula? It's m times e to the negative mx. And what is m equal to? Remember, mu equals 1 over m, which means that m is 1 over mu. So, in this case, m is 1/10. Okay, you can write it as a fraction, 1/10, but I thought maybe you would prefer it as a decimal. That's why I wrote it that way. Okay, let me put that 1/10 right here next to the e. There we go. All right, so let's answer now the three questions. A, what's the probability that the computer part lasts more than 7 years? Okay, so here's what that means. Where would 7 be on here? Let's just put it right here. Okay, and what they're asking for is this area out here. That's the probability of a computer part lasting more than 7 years. The probability that x will be more than 7. Okay? All right, how are we going to calculate that? Well, what we're going to do is we're going to calculate, let me shade this in another color. Let's do it in a brighter blue. We're going to calculate this and then subtract that from 1. Okay, the probability that x is greater than 7 equals 1 minus the probability that x is less than 7. And I showed you in the last example how to calculate this. Okay, that is equal to 1 minus e to the negative m times 7. Okay, so what we have here is we have 1 minus, and then this part here is 1 minus e to the negative 0.7. So what are we going to get? We're going to get 1 minus 1 plus e to the negative 0.7. And the 1's cancel. Our answer is going to be e to the negative 0.7. Calculate that on a calculator. E to the power of negative 0.7 comes out to be approximately 0.497, so almost exactly a half. Ah, darn it. My screen is messing up just a second here. Okay. 0.497. Okay. Look at that and make sure you understand what I did there. Okay, now let's answer B. On average, how long would 5 computer parts last if they're used one after another? Okay, that one's really easy, and we do not need to look at the graph down there because this is actually much easier than it might seem. Let me erase all that stuff down there because we finished part A. Okay, so for part B, it's actually much easier than you might think. On average, each part lasts 10 years. So if you use one part and then another and then another and then another and then another, you're going to get an average lifetime of 10 plus 10 plus 10 plus 10 plus 10. It's going to be 50. Okay, 5 times 10 equals 50. That's literally all you have to do for that one. Okay. All right, now part D. Find the probability that x is between 9 and 11. So just so that you know, let's make sure you understand that question. What they're saying there is, if you pick a computer part at random, what's the probability that that part will last between 9 and 11 years? Okay, that's what's being asked. How do we calculate that? Well, we want to find this area here. Okay, and we do it just like in the last example. I'm going to go ahead and erase this stuff of the questions we already answered so that we have some space here. Okay, so we want the probability that x is between 9 and 11. And the way that we do that is we do the probability that x is less than 11 minus the probability that x is less than 9. And we have a formula for each of those. That's 1 minus e to the negative 0.1 times 11, which will be 1.1. Okay, and the other one's going to be 1 minus e to the power of negative 0.1 times 9, so that'll be 0.9. Put each of those into a calculator. The first one is about 0.667, and the second one is about 0.593, and so what's that going to equal? I should have just done it in my head, would have been faster, but I didn't feel like it. Okay, that's going to be 0.074. So there's about a 7.4% chance that a randomly selected computer part will last between 9 and 11 years. Okay. I think that's all for today. This lecture is getting a bit long. We have another one that we want to do called the normal distribution, but today we'll just do uniform and exponential. We'll do normal on the next one.